Hi everyone, and welcome to the first of two videos going through some past exam questions on enthalpy changes, and particularly calculating enthalpy changes. So what we've got here is a reaction with magnesium and copper sulfate, and we've measured the temperature. We know some stuff about the copper sulfate to start with. We've added an excess of magnesium powder, we've stirred it, and we've measured the maximum temperature. So we've got the temperature change, and it wants us to calculate the enthalpy change for this reaction. Okay, so for this one, we just need to remember the equation that we can use to calculate enthalpy changes, and it starts off with this Q equals mc delta T equation. Okay, now remember, this is not for calculating the enthalpy change. Q is not the enthalpy change, we're looking for delta H. Okay, but Q is the first step. This is just calculating the amount of energy. Okay, and then we need to turn that into an enthalpy change in kilojoules per mole. But we're going to start by doing this. So we're going to do the mass. So what have we got for the mass? If you have a look in this question, there is no mass anywhere. Okay, there is no value in grams. Okay, and this often confuses people. Okay, what we're going to use for the mass is the fact that we had 25 centimeters cubed of the solution. Okay, and we had 1 gram per centimeter cubed. Okay, so we can use that to say if I've got 25 centimeters cubed, it's going to be 25 grams. Okay, it's good here in the question they've told us this. They don't always put this, but even if it's not there, you can assume that the solution will have a density of 1 gram per centimeter cubed. Okay, so we're going to use 25 grams for the mass. The heat capacity is 4.18 joules per gram per Kelvin. And then the temperature change, let's just work this out. I'm going to do it on the calculator so I don't mess it up. It's mental maths. It goes wrong sometimes. 41.5. Okay, so let's multiply that, and hopefully you can see from the units of the heat capacity that this is going to work out and give us units of joules, because we're going to multiply by the grams and we're going to multiply by Kelvin. Okay, one thing I would say is these temperatures are in degrees C, and I've just put it in Kelvin. So have I just messed up here? Well, no, because although we do need to convert from degrees C into Kelvin, because what we've got here is the temperature change, it actually doesn't matter. A change of 41.5 degrees C is the same as a change of 41.5 Kelvin. Okay, because what I could do is convert that value into Kelvin by adding 273, and I could add 273 to this value to get it into Kelvin, but then the difference between the two would still be 41.5. Okay, so don't think that I need to make 41.5 and then add 273, because then you will get the wrong answer. Okay, let's calculate this then. So 41.5 times 4.18 times 25. And we get 4336.75. And that will be in joules. Okay, so that is our value for Q. That's the energy released. But we want delta H in kilojoules per mole. Okay, so if we then divide this by 1,000, that will get it into kilojoules. Okay, so it'll be 4.33675 kilojoules. And then to get it into kilojoules per mole, we need to divide by the number of moles. So how are we going to calculate that? What does it say up here? So it says we added an excess of magnesium. So that means that the copper sulfate must be the limiting reactant. So this is the one that we want to calculate the number of moles of. There's no point calculating the moles of this because there was an excess of it. So not all of it reacted. This is the one we need to use. We're going to calculate the moles of the copper sulfate from this information here. So we're going to do 25 centimeters cubed divided by 1,000 to get it into decimeters cubed, and then multiply that by the concentration. So 25 divided by 1,000 times 0.5. 0.0125 moles. And now we can just do this divided by this to get it in kilojoules per mole. Okay. So delta H is 4.33675 divided by 0.0125. and we get 346.94. Okay, but then we need to be careful because the question was saying do it to 3 significant figures. So we're going to call this 347. Okay, and then it's an enthalpy change, so it needs to have a sign. It needs to be either plus 347 or minus 347. So how do we know what's going on there? We look at the temperature. So we can see that the temperature has gone up. So this reaction must have released heat energy. So therefore it was an exothermic reaction, okay, because the temperature's gone up. And exothermic reactions, delta H is negative because it's given out that energy into the surroundings, and that's why the surroundings have heated up. Okay, so it is really important that you remember to put a sign on at the end. Okay, it's much easier than trying to carry a negative sign all the way through the calculation. So just get to the end, get in the habit of thinking every time I do an enthalpy change, hang on, should it be positive or negative? Okay, part 2 here then says the student weighed out enough magnesium so that it would be in excess. Yeah, we said magnesium was in excess by at least 25%. Calculate the minimum mass of magnesium they would need to weigh out. Okay, so from this then we know it was in excess. So we know that the copper sulfate was 0.0125 moles. And if we go back to our equation, we can see that they react in a 1-to-1 ratio. So to have the right amount of magnesium, we would have to have 0.0125 moles. Okay. If I wanted to have at least 25% excess, then I need to have 25% extra. So I need to multiply this by 1.25. Okay, and that's going to give me my normal amount and then 25% extra. Okay, so let's do that. 0.0125 times 1.25. No, that's a horrible number. 0.015625 moles. And then it wants the mass, so we now need to multiply this by the atomic mass of magnesium to get it into grams. Okay, so we're going to take this number in moles and we're going to multiply it by magnesium's atomic mass is 24.3. You can look this up on the periodic table, remember, but some of these will just stick in your head if you do them enough. And we end up with a mass of 0.379 and so on and so on. 3796875. So how am I going to need to know what decimal places to do it? It says here like it's a 2 decimal place balance. So to 2 decimal places, this is going to be 0.38. Okay, what other questions have we got? Let's have a look. So here we have a definition. What is meant by the enthalpy change of combustion? Okay, so it's the enthalpy change. These definitions, you just need to learn them, unfortunately. But they're nice easy marks if you can remember them. So it's the enthalpy change when 1 mole of a compound is completely combusted. So those are your 2 things that you get a mark for. Mark for saying 1 mole and then a mark for it being complete combustion. If there's any incomplete combustion, then that's not going to be right. Okay, and now we need to do the calculation. So this is actually a very similar calculation to what we've just done, but I hope you can see they've split it up into separate parts for us, which actually makes it a little bit easier. But it's the same question. So calculate the energy released. So to calculate the energy, this is where we're doing Q equals mc delta T. So for this, we need to do the mass. So what is the mass? And again, here we need to be careful. Okay. The clue here is we're using the specific heat capacity of water. So therefore, the important thing is the mass of the water. Okay, and we measured the temperature of the water. Look, everything is about water. So the mass we're going to use here is the 50. We're going to times that by the specific heat capacity. And we're going to then times that by the temperature change. So just, again, do it on the calculator so we don't mess up. 54 minus 20.2, 33.8. Okay, and then times 4.18 times 50. So we get 7,064.2. And that's it. That's our answer to that part. Ah, no it isn't. Ooh, we nearly lost a mark there. Because this is in joules, isn't it? Because of the units here. Okay, and the answer line wants it in kilojoules. So we would have lost a mark there if we're not careful. We need to divide this by 1,000 to get it into kilojoules. So it's going to be 7.0642 kilojoules. That's going to be our answer. So read the question very carefully. Nearly messed that up. Okay. What's the second bit is now calculate the number of moles, and then it's going to ask us to do one divided by the other to actually work out the value. Okay, so this molecular formula, yuck. Okay. Calculate the amount in moles. Really? Okay. So we need to work out the MR of this thing. You couldn't have picked a nicer compound than that for us to do, really. Okay, so we're going to do 12 times 17 plus 32, because hydrogen's just 1, isn't it? Plus 2 times 16 for the 2 oxygens. We get 268. Okay. Yeah. Right, so that is in grams per mole. And then what mass did we have? It must be further up in the question. We had 1.34 grams. So we're going to do that divided by the MR. So 1.34 grams divided by 268 grams per mole is going to tell us the number of moles. And we get 5 times 10 to the minus 3. Okay, and then finally, it wants us to calculate the enthalpy change of combustion. So for this, we need to do this value divided by this value, because then it's going to be in kilojoules per mole. So 7.0642 kilojoules divided by 5 times 10 to the minus 3 moles. 7.0642 divided by that answer we had earlier gives us 1412.84 kilojoules per mole. Okay. Now it doesn't say here how many significant figures we need to do it to, so they shouldn't really mark us down for this. It doesn't say anywhere. So we can pretty much get away with this, so let's just call this 1413. But then remember, we always need to think about the sign. Enthalpy changes should always have a sign. It should be positive or negative. So we need to make a decision here. For this, we need to work out what happened with the temperature. So let's go back up and have a look. The temperature went from 20.2 to 54. Okay, so the temperature increased. So therefore it must have been an exothermic reaction. It must have released energy. So if it's exothermic, delta H is going to be negative.